Okay, welcome to the first of probably two videos about estimation. Now this isn't something that's directly tested on the Regents, but it is a very useful skill to have, and it does come in handy in usually at least one question on the Regents. So I guess it is kind of directly tested now that I think about it. There's a big difference between guessing at something and estimating a value. A guess, the word guess means that in terms of science, if you're trying to guess some measurement or guess the size of something, you're basically just throwing out a random number. You're not thinking about it at all. On the other hand, an estimate is a little bit more involved. An estimate is a prediction that is based on known facts. The difference between the two is that an estimate is based on something. You're putting even just a little bit of thought into it, okay? And there's a process for estimating, which we'll get to in a little bit. For an estimate to be what I would call acceptable, it has to have a few qualities. An acceptable estimate is within what's known as an order of magnitude or a power of 10 of the true calculation. For an estimate, it doesn't really matter if something is exactly correct or not. That's not what we're looking for. What we're looking for is something that's relatively close, and relatively can be a little misleading in some cases. So within an order of magnitude actually means something like this. If you want to estimate, let's say, the length of something, or no, length isn't good. Well, yeah, sure. If you want to estimate the length of something, and that thing is about approximately 100 meters long, your estimate, based on known facts, needs to be somewhere between 10 and 1,000 meters. Now that sounds like a huge gap, and you might be like, well, you'd be way off if you're anywhere within there. But you're within an order of magnitude. At least you're not saying it's 1 meter, okay? You're not 2 orders of magnitude away. At least you're not saying it's 10,000 or 100,000 meters. If you're somewhere within an order of magnitude, that actually works as an estimate. And this makes a lot more sense when we're talking about very, very big or very, very small numbers, okay? If something has a size of like 10 to the 15th and you say your estimate is like 10 to the 16th, yeah, you might be 10 times as big, but you're really not that far off. You're getting in the ballpark. At least you're not saying something like 10 to the 3rd for your measurement. So an acceptable estimate, and obviously you want to be a lot closer than that, and you should be a lot closer than that. Those are the outer boundaries of acceptableness. An acceptable estimate is within an order of magnitude or a power of 10 of the true calculation, and it contains only one significant figure. Any more is needlessly precise. You're worrying too much, okay? The point of an estimate is to make the estimate within a few seconds and then move on, okay? It's more of a guide for solving whatever problem or whatever you're trying to do. It's more of a guide, okay? Estimates are always based on known measurements, so we should list out some known measurements that might be useful to you, that you might be able to remember and say, okay, this measurement is about this big. We've done a few of these before, so 1 meter, getting ahead of myself, is approximately the size of a baseball bat. Pretty much everyone's held a baseball bat before. A golf club. Okay. Even if you haven't held either of those, the length of your stride, when you're walking, is more or less, especially a fast walk. Length of stride in a fast walk. The length of your stride is pretty much 1 meter. Okay? It's not, again, none of these things are exactly a meter, but they're close enough that we can use them as bases for our estimates. Sometimes you might be asked to estimate something in centimeters. 1 centimeter is approximately the width of a fingernail. Okay, all these are approximately 1 centimeter in width. Or another good one is the diameter of a penny. That's another good estimate. A kilometer, which is, again, remember, a centimeter, there's 100 of those in a meter, or 1 centimeter is 1/100th of a meter. A centimeter is small. A kilometer, 1,000 meters, is quite large. The best estimate I've been able to come up with for 1 kilometer is the distance from the town park driveway. Go up past the elementary school and you see the driveway for the town park. to the intersection of Sulphur Springs and Oneida Street. So right down past the middle school at that fork in the road. The distance from the Town Park driveway down to that fork in the road is approximately 1 kilometer. Okay? It's not exactly a kilometer, but it's pretty close. Another way to think of a kilometer is it's a little bit less than a mile. Okay? It's like 2/3 approximately of a mile. All right? Moving on, 1 gram. A good estimate for 1 gram is a paperclip, the mass of a paperclip. 1 kilogram is like a textbook, okay, or maybe like a full metal water bottle, like a full reusable water bottle. And 1 second, a good estimate for that is approximately 1 heartbeat while you're at rest. So these are all references for how big these units of measurement are. And we can use these and other reference points to make very quick estimations and calculations when you don't need to be absolutely correct, you just need to be sort of in the ballpark. Remember that the goal of estimation, there's 2 goals. You want to get reasonably close to the actual answer, and you want to do it quickly. Spending a lot of time on estimates trying to be too precise wastes time. Okay? Now, the process for estimation goes like this. There's 3 steps essentially. First thing you're going to do, let's say we want to estimate the length of 1 unsharpened pencil. First, you decide what units you should use. Do I want to measure this in kilometers? Do I want to measure this in centimeters? Do I want to measure this in meters? You could estimate in any units you want for measuring the length. Okay, so any length units you want, but some would be smarter than others. It would not be very smart to measure in kilometers. Would it be smart to measure in centimeters? Possibly. Would it be smart to measure in meters? Possibly. Okay, so there's 2 options. We're going to estimate in meters because we're a little bit more used to thinking in meters. The second step is determining the order of magnitude. Okay, so order of magnitude, remember, powers of 10, just start with the number 1 and then either multiply by 10 or divide by 10. So it is a unsharpened pencil the same size as 1 meter. Thinking about a baseball bat and an unsharpened pencil, I'd hope you say, no, it's not really that close. Okay, that is actually within an order of magnitude, but we can do a lot better than that. So 1 meter, no. 10 meters, definitely not. Okay, unsharpened pencil is definitely not the same size as 10 meters, approximately. 0.1 meters, yeah, that seems actually pretty reasonable. If you take a meter stick or a baseball bat and you cut it into tenths, that seems like it would be about the size of an unsharpened pencil. So your order of magnitude, you might say, is, okay, so it's around 0.1 meters, but we want to be, we can go 1 step further. We can change that last digit on the, instead of being 0.1, maybe it's 0.2, maybe it's 0.3. What do you think? Once you're done once you're done with this, you just put your answer into scientific notation. So if you end up with, I think it's 0.2 meters long, decent estimate, you would write that as 2 times 10 to the negative first. When you're estimating, the more important part of the estimation is not the number that comes first, it's the exponent on the scientific notation. That is definitely the more important part. We're going to do a few examples in this video, and then we'll cut off and we'll come back with some more examples. And I'll walk you through these estimates. So estimate the lengths of the following objects. Remember the guidelines for estimating, and write your answers in scientific notation. First one is height of an average human being in meters. So the first step is taken care for us for all of these. If we're estimating something in meters, that means we should think about the size of like a baseball bat or a golf club. Those are approximately 1 meter long. How would that compare to the height of the average human, the average adult human? Well, I would say that if you picture a baseball bat and you picture a human, you could probably stack 2 baseball bats and be at approximately the same height as the human. So I might say that the height of an average human is 2 baseball bats or 2 meters. The order of magnitude is about 1 meter, or 1 meter, I should say. And I would say 1 meter isn't good enough. That's, 1 baseball bat is not the same size as most people, but 2 is definitely the same size as most people. 3 is probably a little bit too tall. So, height of an average human being, 2 meters. I would write that as 2 times 10 to the 0, because remember 10 to the 0 means 1 meters. Okay, 2 times 10 to the 0 meters. That's how an estimate is made. It didn't take me that long to come up with that. The mass of an average human being in kilograms. Okay, this one can be a little tricky because sometimes it's tough to estimate masses. If you think of a 1 kilogram as about a textbook, now you can go and do the order of magnitude. Is a human being the same mass as 1 textbook? Definitely not. Human beings have much more mass. What about, let's move up an order of magnitude, 10 textbooks? Probably not. That still seems like it would be not all that heavy compared to a human. What about 100 textbooks? That seems more reasonable, but it also seems like it might be a little bit too big. Okay? Now, you could say 1 times 10 to the second for 100 kilograms, and I would say, yeah, that's an acceptable estimate. We could also move back down a little bit and do instead maybe like 90, 80, 70, or 60 textbooks. Now, that would change the exponent for the order of magnitude, but you would still be reasonably close, okay? And even if you said 1 times 10 to the first for 10 textbooks, you would be within that order of magnitude. So for me, I would say I think a human being is approximately somewhere around 60 to 70 textbooks. So what I would end up writing is this, 6 times 10 to the first kilograms. Okay? I think the average human being is approximately equal in mass to about 60 textbooks. What about the mass of the average car in kilograms? Well, let's see. We said 100 textbooks was a little bit too big probably for the mass of a human, but I think that's too small for the mass of a car. What if we went to 1,000 textbooks? Now it's getting harder to picture how big those textbooks are. I would say that the mass of the average car in kilograms, it's probably somewhere in that range. About 1,000 textbooks could balance out, the mass of 1,000 textbooks could balance out the mass of a car. So I'm going to say 1 times 10 to the third kilograms. Okay, could it be 1 times 10 to the fourth? Possibly, absolutely. But I know I'm reasonably close to the answer. Height of the third floor roof in meters. Okay, now this one can be a little tricky. Third floor roof, so 3 stories. Matter of fact, before we do this one, let's skip down to height of the physics classroom. If you just take any classroom in this building, pretty much, and you think about how many baseball bats it would take to get to the ceiling, I would say, looking around, probably about 3 or 4. Okay, I'm going to go with 3 actually. So let's say that the height of the physics classroom is about 3 meters. I would write that as 3 times 10 to the 0 meters. Now that's just 1 floor. We have 3 floors and probably a little bit of space in between the floors to worry about. So multiplying this times 3, you would get 9 meters, or 9 times 10 to the 0. Let's say that there's a little bit of space between the floors and a little bit of space for the roof. I would say that that's about 10 or 11 meters. Now, we wouldn't write 11 meters because that has more than one significant figure. It's definitely not 20 meters. That would be like twice the height of what the school is. So I'm going to say that the height of the third floor roof is 1 times 10 to the first meters. Okay, approximately 10 meters. Again, I'm making these estimates very fast. Does it matter if I'm exactly on? No, it doesn't. I'm just trying to get as close to the answer as possible. All right, a few more. Time that it would take to drive from Sequoia to New York City in minutes. Any of you who have made that trip before know that it's approximately, let's say, I don't know, 4 or 5 hours. 5 hours is nice because I know that 5 hours, 60 minutes per hour is 300 minutes. And 300 minutes, that sounds like a pretty good estimate. So I'm going to write 3 times 10 to the second minutes. There you go. Time it would take to run a lap around the track. Well, let's see. Are you going to be able to do it in seconds? Are you going to be able to do it in 1 second? Definitely not. Are you going to be able to do it in 10 seconds? No. The fastest sprinters run 100 meters in 10 seconds, and we know that a lap around the track is 400 meters, so that's not even close. The fastest people might be able to do it about 40 or 50 seconds, but for you and I, it's going to take us a little bit longer. I would say that around 100 seconds, going up one more order of magnitude, is smart. If you want to say 80 or 90, that's fine. You just have to change the scientific notation a little bit. So I would say a good estimate for this is about 1 times 10 to the second seconds, 100 seconds. Last one we'll do for this video is the length or width of the physics classroom. Okay? If you imagine how many paces, so one of the examples of how to estimate is with the number of your stride is about 1 meter. I would say it would take about 10, and you can try this in class, about 10 paces to go from one side of the physics classroom to the other. So if it takes about 10 paces, that means it's about 10 meters. So I would say 1 times 10 to the first meter. I'll be back in a little bit to go over the remaining estimations.